what I want to go over today is I want to give you all an image of what the idea of nuclear fusion is and why we want to do this. So I want to do this by giving you a good knowledge of 4 key questions that I think will answer this. So 1, why are we concerned with alternate sources of energy? 2, what is fusion power and why do we want this above others? What has caused delays in fusion and what is the current progress? I'm sure some of you have heard it was 40 years away 40 years ago. Why are we still saying the same thing? And 4, what are the environmental, economical and industrial impacts if we had this technology now? So to begin with, world energy demand is not static, it's rising rapidly. I mean, there are certain things in our timeline that cause it to jump, like the Industrial Revolution, when we start using planes, when people have got readily accessible to cars, the computer age, space age, etc. They cause big jumps. But in general, it's rising rapidly. So why is it rising rapidly? Well, one is the effect of developing nations. Us as a planet, we want to lift billions of people out of poverty. This takes a lot of energy. One of the ways we do this is through building a lot. So for an example, you want to go from, say, a town full of shanty houses to a town full of well laid out roads and houses for your civilian population. On top of this, these developing countries want to become more competitive on the global market with their economy. That also takes a lot of energy. Now in the UK, we did this by burning most of our coal reserves, and it resulted in the smog of London. China is now doing this very same thing, burning all their coal reserves, and this bottom picture just shows you what Beijing looks like 20, 30 years apart. It's obviously a massive problem, and by the Chinese government's own statistics, it's killing 100,000 of their population per year. And for that reason, China's investing heavily in a very green future. So this just reiterates what I was trying to say about the increase in demand. So you can see the top graph shows you in relation to the United States. The green line is where we're at 2010. So China has increased from being quite steady to rapidly increasing. India is now following suit, along with other countries as well. And the bottom one is in relation to the European Union. Now, what else causes this rapid rise in energy demand? Well, it's population. I mean, I don't know about you, but if you've ever seen this graph before, this really shocked me. I mean, the population has been very steady at around 1/4 to 500 million for thousands and thousands of years, and then in the space of about 200 years, it jumps to about 8 billion, and it keeps on rising. Everyone then has access to phones, cars, everyone's using more energy. It makes the demand in energy increase and increase. So how are we going to meet this demand? How are we going to supply the world with fuel? So estimates of our total reserves of oil, gas and coal put them in the region of around 150 to 200 years of reserves left when used together. The red line is the upper limit, blue is the lower limit. The yellow one you see on gas here includes like fracking and shale gas, that kind of stuff. What to know about this is it's a logarithmic graph, which means it's going up 10, 100,000. These are big jumps in magnitudes. Uranium here, we have around 1,000 years left, the yellow one including mining it out of seawater. This is nuclear fission fuel, and breeder reactors here even longer, but they're quite dangerous technology. Lithium, the massive one that you see on the end, where you've got millions of years of it, is what we use to create one of our parts of our fuel. So we've got millions of years left of lithium. But it doesn't really matter what your reserves are of oil and gas or coal, 150, 200 years. What matters is your energy return on investment. What I mean by that is when you discover a new resource or a new pool of oil, you mine the easiest bit first, bit on the top. Then you get harder and harder and harder to mine and transport resources, then harder to find resources. Your energy return on investment goes down. So Uppsala University did a study on coal, oil and gas. I've just picked the coal one here. And the Energy Information Administration of the USA did one on the world oil production. And they both showed that the production of coal and oil will peak around 2050, 2060, where the energy return on investment then starts to go down, so production goes down. So we're seeing a big rise in energy demand, but then the production of coal and oil falling. So that's a big problem. But even if we could burn all of our fossil fuels, that would be a very bad idea, a very, very bad idea. From a environmental point of view, you can see the hockey stick shaped graph here shows the average CO2 in the atmosphere over 1,000 years that you get from rock samples and studying that way. And again, since the Industrial Revolution, it's shot up massively. So we've already raised the temperature of our planet by 1.5 degrees. It's going to go even further, but right now we've done it by 1.5. If we switched off all fossil fuels now, that's what we've got. That leaves the Antarctic ice sheet like this, where the yellow line is the 1997 minimum value. The green line that you can't see is 2005, and there we're at 2007. And that's another shocking image of how much we're melting our polar ice. Then, from a human point of view, as I touched on from China's statistic, from a global statistic, 200 people per gigawatt year are killed each year prematurely from pollution. And that is a massive amount of people, and we can do something about it. Furthermore, from a international relations point of view, if our entire planet is dependent on fossil fuels, we've only got like 150 years left, that increases massive international tension, and you're already seeing it across the world. So, to summarise that, we have a big demand increase in energy, and our supply, yes, we can burn fossil fuels and it'll make up a good chunk of it, up until 2100 maybe. Be a very bad idea, but you could do it. But it's just not going to do anything after that. And to save our planet now, we need something to bridge the gap. So what can we do? Green renewables. Solar power can do it. It definitely can do it. And it really needs investing in. It needs to be developed. And just taking a statistic from, again, the Energy Information Administration for World Energy 2012, dividing that by how much area a power plant in the USA took up, you get around twice the area of Spain that you would need to cover with solar power stations in order to power the world. Might look big, but it's not that big compared to the world. So you can do it. Wind is even more area, around 3 or 4 times as much. But the problem is it's very low energy density. One power station takes 24 kilometres, so you can do it, but it's not that high of a density. Also, how do you get this energy in Scandinavia? I mean, or the north of England? I mean, I'm from Lancashire, and the last time I saw the sun was around 2001. I mean, it's just not viable. We need to, so say you could pave the whole of the Sahara Desert, you'd have to transport the energy, store it. It's the energy density that's the problem. But we need to invest in solar energy because this would make up a huge amount of any sensible energy planet in the future. So, what is fusion? So, fusion is the process that happens in the center of every single star in the universe. It's superheated at the center of the star, 15 million degrees, and the reason we get energy out of fusion is simple. We have the most stable atom in the universe is iron. Right? It's a medium-sized atom. So everything wants to be iron. So your really small atoms want to join and become iron. Your really big ones want to split and become iron. So when the big ones split, they release energy, become closer to iron. When the smaller ones join, they become bigger, release energy, become closer to iron. And that's what happens in the center of the sun. Really small atoms fuse together to create bigger ones, release energy. What we want to do is we want to do the easiest fusion reaction. That's taking the smallest atoms, which is hydrogen. It's the smallest atom that we know of. So what we do is we take heavy hydrogen, which is this one, which is 1 proton, 1 neutron, and super heavy hydrogen, which is tritium, or H3, as some of you guys will be well aware, mining tritium in space, one of your projects, I think, which is this one. So these are both positively charged. So when positively charged things come together, they want to repel. So you have to put in a lot of energy to make them happen. And we do this in the form of heat. We superheat them to about 10 times hotter than the center of the sun, 150 million degrees C. And at this point, they come together They overcome the repulsion, and something called the strong force overtakes and binds them together. That releases energy. So it has to be this hot in order to overcome that repulsion. So at this point, when it's that hot, we call the gas a plasma, and that's what Ricardo was mentioning that I do in my PhD. The sun is effectively a big ball of plasma, just to get you an idea of what it is. So a lot of people ask me, nuclear fission, nuclear fusion, well, we've got nuclear fission power plants, we've already got it, what's the difference? So nuclear fission is, as I said before, the breaking of big atoms, uranium, you get energy. Fusion is the joining of really small ones. It's the opposite reaction. One of the main differences is that in a fission power plant, one reaction explicitly causes the next, which causes the next, which causes the next. It's a chain reaction. It's an explosion, but we control it. It's a controlled explosion. And that's how fission power plants work. Fusion does not work like that. One reaction does not cause the next one. It's inherently safe. There's no explosion to be controlled. One of the other inherent differences of fusion is, yes, you get radioactive waste, right? And it's radioactive for around 100 years. For a fission power plant, their radioactive waste is radioactive for 10,000 years. So it's a lot more manageable to do fusion. Fission, you have to bury it underground for 10,000 years. So one of the other main things as well is it does not promote proliferation. And what I mean by that is to run a fusion power plant, you don't have to stockpile enriched uranium. You don't have to stockpile any sort of enriched material. So it's inherently safe. And one of the other key aspects is per kilogram of fuel, fusion is 10 times more powerful. So it's looking good. What is the effectiveness of fusion then? So what can we do with it? So the fuel, as I mentioned before, is deuterium and tritium. So deuterium is found in water. The planet is 70% water. It's everywhere. Anyone can get it. For every 6,000 hydrogen atoms, there's one deuterium atom. There's loads of it around, millions and millions of years of the fuel. And everyone can get it, which means there's no geopolitical issues on the resources. I mean, there's no one place where deuterium is, it's everywhere. But the problem is, tritium isn't. There's none of that around at all. It's radioactive, it decays with a half-life of 12 years. It doesn't stay around for that long. So we have to make it, and we make it in our reactors. And I'll go on to talk about how we do that later. So just to get you an idea of how much energy we can get out of this fuel, half a bathtub of deuterium plus the lithium from one laptop battery would give enough energy for one person for 30 years. That is a massive output of energy and completely off the scale compared to coal, oil, or any fossil fuels. So how do we go about controlling a star on Earth? I mean, it's 150 million degrees C. You definitely can't touch it. So what we do is we have what's called a fusion triple product. In order to get gain out of our reaction, we need to have high enough temperature, so the atoms actually collide and fuse, high enough density, so there's enough particles, so enough of them actually happen, then a high confinement time, so it happens for long enough that we get fusion power out there. So we do that in two main routes. One's inertial confinement fusion, where you use massive powerful lasers to implode a target, so you get really high temperature, really high density, but it's over in a nanosecond, but you still get gain out of it. Or there's magnetic confinement fusion, so you get lower density, still the 150 million degrees C plasma, but over a longer time. We want to keep it for hours and hours hot like this. And this is the most advanced prospect to date. They're called tokamaks. The most advanced one is called ITER, which is being built in the south of France. Some of you may be aware, not too sure. So this is what the tokamak actually is. As I said, plasma, 150 million degrees, can't touch anything. So what do? We use magnets to suspend it in a vacuum. It doesn't touch anything, it's suspended. To give you an idea of how this works, if everyone could just put up their right hand like this. So imagine your thumb is the magnetic field. That's the way the magnetic field goes. And your fingers are the particles. If you curve round in a screwing motion, like you're screwing a screwdriver, then these particles are going round the magnetic field, so they're confined, right? But they can still escape out the end. So what do? Wrap it round on itself, like a donut. It can't escape, they're confined. And that's what this is, a big donut shape of this superheated plasma suspended in midair using magnets. So this takes a lot of energy to do. You've got to heat it to 150 million degrees, and you've got to use magnets to levitate it. So how are we getting power out? Well, we define something called the Q, which is the ratio of the fusion power that you get out divided by the power that you have to put in to make it. So you want this to be above 1, right? Otherwise you're not getting anything. So I've got a small video here of JET. JET is the Joint European Torus, which is in the UK. It's the world record holder for the largest fusion gain so far, led by the UK, and it just shows you a quick image of what it actually looks like inside the reactor. So first off, you'll see it start to ignite here. All the coloured bit is obviously the plasma, and inside is the plasma as well. The coloured bit is actually the coldest part of the plasma. That's why you can see it. That's the coldest part. The stuff that you can't see is the hottest bit. So that's just a snapshot of one side of a JET tokamak. So that's all well and good, but you've got this fusion reaction, this nuclear reaction. How do we harness the energy from it? Well, this is the reaction that I said that we want to do. This is the nuclear physics that I get so excited about. And this reaction gives you a lot of energy in the form of a helium and a neutron. So the helium, positively charged, it stays confined in the magnetic field. It uses the energy from the reaction to heat the plasma continuously. And when it does that, we can now turn off our external heating because the reaction itself is heating the plasma itself. Okay? So that gives us a bigger Q. We can turn off this heat, we're just left with the power of the magnets. Get a bigger Q. So that's what we want to do, it's called ignition. The neutron, that carries most of the energy, is neutral, so it's not confined by the magnetic field. Shoots straight out, hits the wall of the reactor. This converts into heat, which we then use to, along with the heat flux coming from the plasma, like a radiator, if something's hot, it heats you, heats the wall, which heats water, which then, as in every single other power station, turns a turbine to make electricity. It's basically a space-age way of heating water, which is a Victorian way of generating power. But, I mean, you can't solve all problems, can you? So I want to talk to you a little bit about tritium. I touched on it before. That was one of the snags. It's not readily available. As some of you will know, there's only 2.5 kilograms in the world, and Canada has most of that. They make it in their CANDU reactors, which are a byproduct of their fission reactors. It's worth $30 million per kilogram. Expensive stuff. So we need to make it. So how do we do that? So lithium's the third most abundant thing in the universe. There's millions of it around, millions of years worth of it on the planet. So if you hit a lithium atom with a neutron, you get a tritium atom. Well, luckily, we've got a neutron from our reaction in our reactor. Great. So the neutron, also not confined by the magnetic field, hits the lithium in the wall, creates a tritium atom. Tritium goes back into the fuel. So no tritium is brought to site and none leaves. It's made and used in the reactor. So I have a short video, well, not video, but like illustration here from Culham Centre for Fusion Energy in the UK. So this just gives you an idea of how it's going to work. So here's our plasma. Here's our source of heat. In a normal power station, that would be your coal, oil, or gas. In a fission reactor, that would be your uranium. That's what generates the heat. This heat heats the water, which then turns to steam, turns your turbine, electricity. Your deuterium, found from seawater, comes in from the outside. Easy to get from seawater. Anyone can do it all around the world. That comes in, along with the tritium, which is made from your breeders in the side. So your lithium comes in from the outside, it's turned into a tritium, which comes in here, back in, lithium, tritium, back in. And the waste product is helium, which you can bottle up and sell, which is great news. Just to summarise, if you ask yourself, what would be the perfect fuel source? What is that? How is it defined? Well, it's one that takes up very little space, very high energy density. It's one that has no greenhouse gases, one that has very manageable physical waste, and one that everyone can use. And that fuel source is fusion. But there's a catch. Well, there's always a catch, isn't there? I mean, why have we not got it? So fusion is really, really hard to do. It's the hardest thing we've ever tried to do. To put it in perspective, I mean, the space race, that took 2 individual countries around 20 years to get into space, put someone on the moon, right? This has taken the entire planet around 60 years. It's very, very difficult to do. You can split the different difficulties into 3 different sections. One's the materials. So I'm not going to gloss over any of this. I'm going to give you the cold, hard truths. We need materials in the wall of the reactor that last 10, 20 years, right? They're being bombarded by these high-energy neutrons. It's causing them to go brittle and deform, and they're not lasting more than around 2 or 3 years. So it's a big challenge. We need to do that. It's also got to withstand a heat load, which in some instances can be as high as a rocket engine. It's very high heat loads. So we need to develop that. The second one is plasma confinement. The plasma isn't just staying there like a happy little ball of gas. It's really turbulent. And one idea of turbulence is when you pour your milk in your really hot coffee and it bubbles around. It's exactly what the gas is doing, bubbling around. And you have instabilities. So the plasma wobbles, and we've got to hold it there. We're holding it in mid-air with magnets. It obviously wobbles and moves. Turbulence is something that we did not know about in 1980. It's one of the reasons why we're making the reactor so big now, and one of the reasons why it's put fusion back 40 years. People made bold claims. They didn't know about turbulence. They didn't know about instabilities. The next one, superconducting magnet design. So we need a superconducting magnet to hold our plasma in place. This is by far the biggest cost. It's around half the cost of the entire reactor, just on the materials to make this. It works at about 2 degrees Kelvin, which is minus 271 degrees. So here we have our plasma, 150 million degrees, and about this far away, maybe a little bit more, is minus 270 degrees. That is a big engineering challenge. That is the biggest temperature gradient in the universe that we know of, and we're trying to build it on Earth. To make these magnets at the moment takes really rare earth materials. So although the fuel is abundant, anyone can get it, no geopolitical issues, to make the magnets isn't. We need people that can make high temperature superconducting magnets which use different materials, and that is a key area of research. So on the left is how powerful your magnets are for confining the plasma. On the right is your heat, how hot you want to get it. You've got to get a nice little balance so it doesn't disrupt. You get these instabilities which I was talking about, which we didn't know about in the 1980s, but we do now. And you have to somehow control them by pressing this little button that comes up at the bottom. The idea is you want to keep this controlled until this time runs out. The time is just how much time's left until you've got an economical machine. So if you can all get in your groups there, if you can operate it until it's economical, then you all get a Haribo Star Mix. Right. How did you all find that? It's pretty difficult, isn't it, trying to get the balance? It's, yeah, it's like having a little spinning top and trying to keep it spinning. You want to keep it in the key point of balance, and it's quite difficult, especially when all these instabilities crop up, which you then have to zap with your big fat lasers. So I spoke a bit about why fusion is the perfect fuel source, and also, without covering up any details, why, what the catch is and why it's so difficult. So how are we going to address this? So the next big step is building a machine called ITER. So far we have a current world record held by Jet in the UK, the video I showed you before of the tokamak. That got a Q of 0.67. You might think, great, didn't actually break even. But it's the high, we've already done fusion. We've already got fusion power out. That's not the hard bit. Yeah, in fusion, anyone can get fusion. You can do it in a high school in a lab experiment, right? What's important is getting the ignition, and that is what we're going to demonstrate in the new device being built in the south of France. Quite a nice place to put an experiment, to be honest. So, yeah, we want to get 500 megawatts out for 50 megawatts input, a gain of 10. We want to maintain that plasma for 400 to 600 seconds. You know, we're making steps. The end goal is holding it for hours, right? So what is ITER going to do? So it's going to demonstrate a combination of all the technologies that we have been developing across the world in our global efforts so far. It's going to demonstrate breeding tritium within a reactor. We're going to use up all the world's tritium. We're going to do it. It's going to go in that reactor, it's going to be on left. So every device after this has to breed its own tritium, unless you guys bring us some back from space. That'd be great. What else it needs to do is it needs to demonstrate that we can maintain this plasma, and we've learnt from the instabilities and the turbulence that you just all saw on your little game. And that's what ITER will do. So why has it taken so long? I mean, ITER was started in 1988. That's when the first idea came. But from a business perspective, it's a massive risk to do a fusion experiment, which was largely untested. Largely, nobody knew how to handle a plasma. No one had done it before. It is absolutely unprecedented. So how do you handle this risk? You split it. You get 35 different countries all to chip in. It's no longer you that's holding that risk. It's split. But that comes with its own unique challenges. One, when you've got 35 different countries, everyone's got their own idea of where it's going to be located. Canada would have been a brilliant idea because they've got all the tritium. You know, other people wanted it other places for different ideas. That took a long time to discuss and iron out. Again, what the mission goals are. Every country had its own different mission goals. How do you iron that out? And every country had its own idea of how we're going to design and operate it. So it takes a lot of deliberation, especially on the political level. So that set ITER back over a decade of this deliberation. The next thing is we have to write from scratch all the international law and legislation on nuclear fusion. There isn't any law. It's never been done again before. You've got to write all the law from scratch, and we've done that. So despite the fact that it's put ITER back by around 15, arguably 20 years, we've now ironed out all the legislation. It doesn't have to be written again. You've written it. We're now not ever going to do it in this sort of massive collaborative effort anymore. We've got the knowledge. It's now acceptable for one business, one country to undertake the risk on its own, less deliberation. The biggest hurdle with fusion is the funding. It is massively underfunded, incredibly underfunded. You might have heard that a lot from a lot of different people, but I'll tell you why. So here's just a few things that cost more than fusion. So, the London Olympics cost more than ITER's entire lifetime from design, construction, running, and dismantling. London Olympics cost more than that. The Iraq War is more than the total fusion budget of the world. What BP put down to deal with its oil spill in the Gulf was around, 30 billion? That's more than the ITER lifespan, again. And quite a funny one, 1 week's worth of Halloween costume buying in the United States is more money than the whole of the fusion budget. Other than America. So, yeah. Just to put it in perspective, for about the 10 trillion, the 10 billion euros that is funding ITER, that's 0.2% of a 5 trillion euro energy market. Now, just to give you an idea of what the ratios are here, obviously as a business, you know you have to spend money on research and development to get a product to sell. So how does this compare to other markets? Well, pharmaceuticals spend about 20% of their income from sales on R&D. Aerospace spends around 11% on R&D as a function of sales. Computers is around 8%, and here's energy at the bottom. That's not fusion, that's energy as a total, 0.4%. How do you get a product if you don't spend anything on the research? You don't. So, what's our timeline to a fusion power plant? We're pretty confident that we know how ITER is going to operate. Back in the 80s, we had all the funding coming out of the Cold War and the 1960s. We had a lot of money, but we didn't have the knowledge. Now, we have the knowledge, we just don't have the funding. And that's what's putting it back. So despite that, we're pushing ahead anyway and trying to get a product out, despite the 0.4% funding. So ITER will have a first plasma by 2025, and hopefully it will have demonstrated its goals, so the tritium breeding, the plasma control, by 2040. Now, in the meantime, we are designing and building demonstration power plant. These timelines aren't stacked one on top of the other. You do one, you do the other. So we are designing and building demo. That will be built by 2050. And you can see the size of these things going up. The reason the size of these things go up is because turbulence and instabilities mean that it has to do that. And that's what we didn't know about in the 80s. Demo will be the first one to put fusion power onto the grid as a demonstration power plant. It will provide energy to the grid. ITER won't. Even though it has 10 times more power out than you put in, it's purely an experiment, the most expensive experiment ever built, more expensive than CERN. So, in the meantime, along with this, we have something called if-MIF. Now, as I said before, materials are one of the biggest problems. Along with plasma, it's a game killer, really, if we can't figure that out. So, ITER will solve the plasma problems and hopefully test a few of the materials configurations. if-MIF will test all of the components that we need. It will test the materials. It's a pure materials testing facility because we need to crack this. So if we, along this timeline, demonstration power plant built by 2050, commercialization will happen between 2050 and 2070, which is when we need it. Or we need it now, to be honest. So I'm sorry to hit you with a big wall of text. Couldn't figure out another way to do this. But just to summarize, the world has worked together. And yes, it's set back ITER quite a long time, but we've ironed out all the creases. We've done the legislation, and we've learned together as a community. And that will obviously speed up the progress in the future. Funding is the biggest problem. We have just not got the funding. Like, we should not technically be making any progress with our amount of funding, but we are. We're pushing forward. ITER will hopefully, for this reason, China is, well, they're throwing money at everything at the moment. So they're throwing a lot of money at their own version of ITER and doing it on their own. And they're putting in a lot more money than we are. And they aim to have it on a much faster timescale, 2030. So ITER, their first plasma, will be by 2025, hopefully have the goals by 2040. Demonstration power plant built at the same time, done by 2050. Commercialization will happen between 2050 and 2070, but that's only once you've convinced the general public that it's economically viable and it's safe. Key one being safe. So what is the impact of fusion if we had it right now? Well, for starters, you can completely get rid of all your fossil fuel generators. You would slash your carbon budget and therefore increasing your economy. You cannot understate this point. You have clean, breathable, fresh air and slowing down significantly climate change as it is right now. As I said, it kills 200 people per gigawatt year, or from China's own population, 100,000 a year. This is something that you cannot underestimate. So how much does it cost to build a fusion power plant? Well, you can only make estimates, right? So a good estimate would be how much it costs to build ITER, right? That is basically what we'll have. So ITER costs around this, just a bit less than a fission power station, advanced fission, which is advanced nuclear. Advanced nuclear is here. with wind, offshore, solar up here. That's how cost competitive we imagine it will be based on how much it's costing to build our ITER at the moment, along with obviously the maintenance and the cost to get it on the grid. Now, what's this worth to industry or people involved in it? Well, if we had fusion right now, we cracked it, whoever was involved in cracking that can sell their expertise to a market value worth trillions. That, again, cannot be underestimated. So who's involved with this right now? We have lots of industrial involvement from startup companies. They want to build their own fusion reactor. We have, close to home, there's Tokamak Energy. They've raised 25 million. And on the other end of the scale is, in America, Tri-Alpha Energy, raising 140 million from private investors. It's startup companies trying to do it on their own. And this is exactly what we need. It's not going to be academia or government spending that solves fusion. It's going to be you guys. It's going to be industrial involvement. So what other way? You don't have to just build a nuclear reactor yourselves, right? You can get involved by contracting, and that indeed is exactly how ITER is being built, through contractors. So, especially with the components test facility, I was just speaking to one of you then who's got really valuable knowledge on materials. Like contracting for the materials testing facility will be invaluable. It would be industrial involvement that we need. So if you want to speak to me about contracting for the different nuclear experiments that we're doing, then speak to me later. So at the start, I tried to answer your 4 key questions. Why are we concerned with alternate sources of energy? Well, it's the dwindling fuel reserves, the demand increase, the rising population, and the big one, global pollution. Why fusion? Any successful energy plan will involve a significant amount of solar energy and green energy, what we're doing at the moment, that needs to be invested in. But it will also include fusion energy. That will take up the main bulk of it. It's on-demand energy, and you can use it anywhere. It is, if we crack it, the perfect energy source. It is obviously got a catch. It's incredibly hard to do, but I think as a planet, we are up to the challenge of making this work, and the benefits completely outweigh all of the effort that we have to put in to crack it. So what has caused delays? Well, we didn't know about turbulence and instabilities 40 years ago. It's unprecedented to build a nuclear reactor on this level. International deliberation on location and design has put it back quite a few years. But the biggest one is funding. I mean, as I said, 40 years ago, we had all the funding, not much of the knowledge. Now we've got a lot of the knowledge, not much funding. You cannot get something out if you've got 0.4% of the total cost coming in on your R&D spend. It's insignificant. So what are the environmental, economical impacts? Then, environmental is obvious. We can turn off all our fission power plants, clean air, hopefully try to plateau climate change. And in terms of industrial impact, if we had it right now, you would be able to sell your expertise to a £1 trillion market value. So, thank you very much. I invite any questions and a big discussion now from you lot.
So, my question is about the lithium.
Mm-hmm.
Isn't it right that the 90% of the lithium is in just one country of Latin America, and that China is basically buying all those mining areas and closing them up until they feel like using it? And wouldn't that cause political issues and political tension between countries? Because for this generation, at least, lithium is a key element for this to work.
Yeah, you're exactly right. It is definitely a key element, and if they are in different corners of the world concentrated, then could cause international tension. I wasn't aware that they are so concentrated in different areas, so I'll have to speak to you about that later.
So my question kind of piggybacks off Trace's back there, kind of combating the multi-billion corporations that are up against you guys, whichever way they come at you. But has your community thought about going out and doing anything as far as crowdfunding, taking everybody from the United States and telling them to reuse their Halloween costumes from last year and set that funding aside for you guys, because I mean, doing that for the entire world, I think there'd be people out there willing to donate a few bucks to the cause.
Yeah, no, I don't think that we are. Obviously, we have a lot of very important speakers that go out to give talks. You're all aware of the TED series of talks. Steve Cowley, who's the head of Cullum Centre, has done a very, very good TED talk. So we're getting the word out there. We have an outreach officer, which is one of the doctors at York Plasma Institute, whose main job is to go out and spread this word on fusion. She goes to all from schools all the way to multinational businesses to speak about this. So yeah, it's all trying to build awareness and educate people on what the current situation is with the planet's energy. So yeah, I'm sure we're seeing quite a significant awareness now. Now people know what, if you say fusion, people have heard it. I don't know what it is, but maybe 10, 15 years ago, if you said fusion, they're like, what? You know, now they've heard the word, it's getting more aware of it.
Nuclear fission is kind of restricted as to which countries can use it. What's the plan for fusion? Would it be more openly available?
Yeah, that's a very good question. So that's one of what I see as the key advantages of fusion. So as I touched on before, for fission reactors, you have to stockpile your enriched uranium. There's been international tension over that. Like, are you stockpiling enriched uranium to, do something bad with it, or are you trying to actually make power out of it? Fusion, you don't have to stockpile anything like that. I mean, obviously, there are ways to use fusion as a weapon, but there's no specific material that you have to use. So in that sense, I wouldn't say that it's controlled. Obviously, you can't just now, if we had it now, just drop a nuclear fusion reactor in Nairobi or something. I mean, you've got to be confident that you know the area that it's going to go to can use it in a good way. But it is inherently safe as a fuel source. That's the main thing. I mean, if our magnets just failed, then the plasma drops to the bottom of the reactor. You've melted the bottom of the reactor. That's it.
We're constantly being told over here that we have big peaks and troughs in consumption. So people putting the kettle on when EastEnders finishes and that kind of thing. How does fusion react to that? And because I know they're cycling things like gas turbines more now because of the constant power that they have to take in from solar and wind. How does fusion sort of react to that cycling?
Right, yeah. So that's, again, one of the main things about fusion. You can turn it on and off. It's like any other power station. So I know at Cullum, they're not allowed to do a plasma shot on jet during the adverts of Coronation Street because it takes too much energy and everyone wants to put the kettle on, right? And there are these big spikes. So what we do now is we just turn on a reactor for the period of the kettle brewing, turn it off again. You can do that with a fusion reactor. Just turns on.
So you mentioned the size of the reactors getting bigger because of turbulence.
Mm-hmm.
What does that mean fundamentally for the likes of fusion rockets and using fusion as an actual method of drive and transportation in the future? Assuming we get it down as it is and we kind of nail it.
Oh, so using this as a fuel source for like space travel or something like that, making it smaller. Yeah. So when I spoke to you about the confinement, they're confined around the magnetic field. The turbulence causes it to move field lines and escapes outwards. That's why we have to make them bigger, so confinement time's larger. Now, I know when I put on some of these startup companies, some of them have, well, for example, this is what's called a spherical tokamak, as compared to a conventional tokamak. That's what I work on, a spherical tokamak. They are a lot smaller and a lot cheaper to build, right? On the other end of the spectrum, there are other companies trying to work on different ways of creating fusion with small, compact fusion devices. So right now, what we have to focus on is making the thing work. Then we can focus on refining it. So in terms of a compact fusion device that you're going to want to put on to maybe a spacecraft or something like that, we're quite far away from the spacecraft anyway, but it will be a long, long time after that, because it is one of the fundamental reasons why tokamaks are getting bigger. But yeah, one is the spherical tokamak. which is smaller, works in a slightly different way.
I've got a personal question for you, Matt, if that's
Yeah.
okay. Considering that we have our talent here and our future leaders in the business, and we also talked a little bit about career and progression and stuff like that. I mean, in our business, if we do a project, it's kind of automotive maybe 2-3 years out, aerospace maybe a little bit longer, but you have this end point in view.
Yeah.
When you personally talk about commercialization in 2050,
Yeah.
well, part of the question is, how do you plan your career? And how do you motivate yourself to actually, I mean, in 2050, you won't be 25, 30 years anymore. So how do those timelines work for you personally in your career?
Me personally, so I've spoken to a few of you a little bit about this. I had a massive career change. I was in the Air Force first, and then the recession hit. I had to, there was no more jobs anymore. So I did a complete 180 and went to Fusion. The reason I picked this is because I wanted to do, call me like, it's a bit tree huggery, right? But I mean, I wanted to do something which I felt that made a big difference to the planet. It scared me when I saw how fast we were using up resources. I mean, everyone's naturally, they want to keep their resources, don't they? I mean, like when you're a kid, you always save the best bits to last or something like that. You know, you're all inherently aware of resources. So it scared me, and I wanted to do something that would contribute to solving that problem of resources and also solve the problem of global warming. So for me, I'm really happy to be involved in that, and that's sort of why I'm on the fence between academia and industry, because academia, I can research what I want and I can go into following my interests like this. Industry, it's a little bit more restricted. But yeah, my career path I see in the future, I'm on the fence between industry and academia for those reasons. But the reason I got into it is purely for that.
Just thinking, the climate conference in Paris was not so long ago. Was this...
The what conference, sorry?
The climate conference in Paris. Was this discussed, and what were the reactions?
I should definitely hope this was discussed. Certainly it will have done, especially by, the European Union. This is the one in the UK which has broken the record or holds the world record, is the joint European Torus. And the ITER project is a global effort. I mean, Europe are putting a lot of money into it. So the amount of money that are investing, they're all well aware of this project. This is a worldwide effort and a big money spent, so they will have definitely discussed it. But as I said before, fission, in order to bridge this gap, this is like 2050, 2070, right? We do not want to burn significantly more fossil fuels on the way. We need to invest heavily in solar and wind and other renewables. Also build fission reactors, because they don't produce greenhouse gases. There's radioactive waste, but they don't produce greenhouse gases. So yeah, I'm pretty sure that the outcome of that would have been to see a future of significant spending on green renewables we have right now to bridge the gap as we go. And then for a more long-term goal, like that, what we're going to do to meet all of our energy demands all the time, then this is the long-term goal that they would have discussed.
So my question now is, if there was more funding, would the development time be reduced?
Yes.
So it's not so much about how time it's needed to actually develop it, but it's really dependent on the money.
Yeah. So the people solving these problems are PhD students, postdocs, professors, lecturers, along with collaborations with some of these startup companies in industry, right? So if you've got, say, a number of problems this big, and you've got this many people working on it, because that's all you can afford, you've got to do these first, and do these, then do these. The more money you've got, the more people you've got working on these problems. And we're not short of intelligent people to do this. We're not short at all. We just can't pay for the spaces to fund their research. It's also like building the reactors as well. I mean, the speed at which you build these is dependent on how much funding you've got. I mean,
yes.
Yeah.
So the next question for that would be, if there was enough money for this,
yeah.
what would be the time to actually be able to build this and have it in the commercial stage?
If we had all the money that we wanted, let's make sure I don't make too bold of a claim. Watch your video on me. So, I guess the answer is, like, how badly do you want it? I mean, like, if you could put all of your resources and all the money in the world, like, say if we needed to do this, otherwise it's going to make a world disaster in 20 years, we'll have it in 20 years. Like if we were so pressed to do it, we would do it. So it scales with the amount of resources you throw at it, the timeline goes down. So there's no like, oh, this is like the minimal time. I mean, it's not, you can throw all your resources at it, it's not going to be ready in 5 years, right? It's going to still take maybe 10, 20 years. You've got to build this reactor, you've got to learn from it, right? But if we had all the money, all the resources, we could build another reactor working in a slightly different way, running at the same time as ITER. You know, learn double the amount and have it ready even faster. So yeah, it kind of scales money, time like that. Yeah. Yeah. All right. Yeah, thank you very much.